Okay, so now that we have this whole framework, let's see how we can apply it to an inventory problem. So an electric power transformer manufacturer predicts its demand over the next 4 months to be 1, 3, 2, and 4. So this is the demand in each of the months. So month 1 is 1, month 2 is 3, month 3 is 2, month 4 is 4. Transformer units respectively. It currently has no units in inventory. In order to meet the demand, it has to decide whether to produce all the units at once, just the number of units required in each month, or somewhere in between. So this is a long-winded way of saying how much should you produce each month. What makes the problem challenging is that there's a holding cost of $500,000 for every transformer in inventory at the end of the month. There's also a $3 million setup cost for every month in which a unit is produced. If you're going to produce any, you got to pay $3 million. And it costs $1 million to manufacture one transformer. There's enough storage space to hold up to 4 units and sufficient production capacity to produce up to 5 units. What is the optimum production schedule? This problem can probably be formulated as an integer programming problem, as an exercise. One could do that. But we're going to solve it here with dynamic programming. And just knowing what we know about integer programming and its sometimes unpredictable performance, it's worth looking at some alternatives. And also it's an illustration of dynamic programming for teaching purposes. So where do we go with this? We need to apply it to the framework, so let's apply it. We're going to have all the same concept as we had before. Let's concentrate on the important ones. The important ones is the stages. We definitely need to know what the stages are. N means a month, and that's 1, 2, 3, and 4. We need to know that the state variable is the number of units in inventory at beginning. So this is very important. The timing is important. It's very easy to get lost in terms of timing. So the beginning of the first month, that's why the beginning of the first month, S1 is 0. But any of the other months, including the 4th month, you could start that month at any given level. We don't know what the optimum level to be is at the beginning of the 2nd, 3rd, or 4th month. So you need to know this state variable, and you need to know the decision variable, which is number of units produced during month N. So that's that symbol, that's the X in this case. We're always going to use S, so we're always going to use X. Now these 3 that I've starred are definitely, you definitely need to do them for every problem. And then you may want to go straight into solving the problem. What happens is if you do them by hand, any of the things that I haven't talked about, you can figure out as you go along. And this will become clear once we start doing the problem. But if you're going to ask someone to program it, then you have to be more, the specifications need to be more complete. So then you need to spell out what are all the possible states, and you need to point out what's the limit on production. So you cannot violate this constraint, this expression. So you can move the other variables to the size of the limits, but this is how it's expressed, and you cannot produce more than 5. The transition relationship is what you currently have plus what you produce minus the demand, and the immediate return is if you don't produce any, it's just a holding cost, $500,000 per unit. And if you produce, then have to pay the fixed $3 million. You have to pay $1 million per unit produced plus the holding cost. And we'll talk about when the holding cost is incurred. That isn't stated here. So let's go and solve the problem by hand, and we'll do that in the second video.